In this series of lectures, I am going to describe the perturbation theory in quantum mechanics, both the time-independent and the time-dependent versions. Perturbation theory, of course, is a very important part of the calculational tools in quantum mechanics for the simple reason that most quantum mechanics problems that are of any importance cannot be solved exactly. Perturbation theory is one very important way of getting controlled approximations to the final answer in such situations. So let us start by describing the setting for time-independent perturbation theory. This essentially involves the problem of finding the spectrum, which means eigenvalues and eigenvectors, of the Hamiltonian operator H. Most often, perturbation theory is couched in the language of the spectrum for the Hamiltonian, although you must realize that you should be able to use similar ideas for other Hermitian operators as well. But be that as it may, we are going to talk about the spectrum of the Hamiltonian here, and H, this Hamiltonian, the Hamiltonian for the full system, has presumably has eigenkets Shayan and corresponding to energy eigenvalues En. Now, our aim is to figure out what the Ketchayans and Ens are, given that we can decompose this Hamiltonian H into two pieces, H0 and V, where the spectrum of H0 is exactly known. So, H0 is an so-called exactly solved Hamiltonian. So, its eigenvalues are epsilon n in my notation, and the corresponding eigenkets or eigenvectors are phi n. So, we know the epsilon n's and phi n's exactly. V, the rest of the Hamiltonian, is in some sense small. That is, we expect at least that because of this additional piece V, the eigenvalues and eigenvectors of H will differ from the eigenvalues and eigenvectors of H0, but not by a huge amount. So, perturbation theory essentially allows us to calculate corrections due to this perturbation V to the unperturbed eigenvalues epsilon n and eigenkets phi n. So, we want to figure out how Shayans are different from phi n's and how Ens, the exact eigenvalues of H, are different from epsilon n's. Now, to solve H Shayan equals En Shayan, what we do is we first introduce a formal parameter lambda by writing H as H0 plus lambda V. Of course, this means that when lambda is 0, we have our exact problem, that is H0 whose solutions we know exactly, and our actual problem, the problem which we really want to solve, is the one for lambda equals 1. Here lambda is really a formal parameter. It's meant to keep track of how many times V is appearing in a result. Now, in the Rayleigh-Schroedinger perturbation theory, which we are describing right now, we make a basic assumption. The basic assumption is that the energy eigenvalues and eigenkets of the full Hamiltonian can be expanded in a power series in lambda. So, En is En0 plus lambda En1 plus lambda square En2 and so on. Notice that these 0, 1, 2 up here are not powers. So, that is why I have just written them in brackets to remind you that this is not En to the power 0, En to the power 1 and so on. These are the 0th order, first order, second order corrections to the unperturbed energy eigenvalue. Of course, you can write this using the sigma notation in this form as lambda to the m, En_m, where m runs from 0 all the way up to infinity. Well, we assume the Shayan can be expanded in a similar manner. So, the Ket Shayan is the Ket Shayan 0 plus lambda Shayan 1 plus lambda square Shayan 2 plus and so on. So, it's a series, infinite series in parameter in power series in the parameter lambda with terms Shayan 0, Shayan 1, Shayan 2, etc. These are all eigenkets, and the Shayan 1, Shayan 2 of course are the first order, second order and so on corrections to Shayan 0. So Schrodinger equation for H, this H0 plus lambda V, simply becomes H0 plus lambda V acting on this infinite sum which is Shayan equals this infinite sum which is of course En times this infinite sum which is Shayan. So if I just were to write this out in detail, this is what it would look like. H0 plus lambda V acting on Shayan 0 plus lambda Shayan 1, etc., etc. is equal to En 0 plus lambda En 1 plus lambda square En 2 and so on. Now comes the, now you can see the utility of this lambda parameter, despite the fact that we are going to put in lambda equal to 1 in the end. The parameter lambda gives us a very nice way of looking at this equation order by order. So if this is going to be an identity in lambda, it has to match for all parts of lambda. So you can compare powers of lambda on both sides. Say the term which is completely independent of lambda, that is the term which has the power lambda to the power 0, on the left is simply H0 times Shayan 0 acting on Shayan 0, right? Every other term on the left hand side has at least one lambda power. What about on the right? On the right, the lambda independent term will be En 0 times the ket Shayan 0. So this is the equation we get by comparing lambda to the 0 on both sides. By comparing lambda to the 1, well, you get lambda to the 1 in two ways on the left hand side. You get it from H0 acting on Shayan 1 and V acting on Shayan 0. That's the left hand side. What about the right hand side? You get lambda to the 1 by taking En 0, which has no lambda, times Shayan 1, which has exactly 1 lambda with it, plus En 1, 1 lambda, times Shayan 0, no lambdas. So matching them both, this is the equation that you get from the first order perturbation term, lambda to the 1. Well, what about lambda to the 2? Well, on the left you get H0 Shayan 2, that gives you lambda square. Another term which gives you lambda square is V Shayan 1. What about the left hand side? That was the left hand side, sorry. What about the right hand side? You get En 0 Shayan 2 lambda square. En 1 already has 1 lambda, that goes with Shayan 1 to give you lambda square, and En 2, which already has all the lambda powers you need for lambda square, gets paired with Shayan 0. So for lambda square, this is the equation that you get. Well, for lambda cube, similarly on this side you get H0 Shayan 3 plus V Shayan 2, that gives you the 2 lambda cube terms on the left. There will be 4 lambda cube terms on the right, En 0 Shayan 3, En 1 Shayan 2, En 2 Shayan 1 and En 4 Shayan 0. And we can go on like this. In general, for lambda to the m, the mth order perturbation equation in Rayleigh-Schroedinger perturbation theory is H0 acting on Shayan m plus V acting on Shayan m minus 1. So on the left you get only 2 terms, simply because there are only 2 terms in this H0 plus lambda V. On the right, on the other hand, you actually get m plus 1 terms. En 0 goes with Shayan m to give you lambda to the m, but En 1 goes with Shayan m minus 1 and so on, all the way down to En m going with Shayan 0. So these are the basic equations in Rayleigh-Schroedinger perturbation theory. Now let us focus on these equations, at least the first few of these equations, term by term. The 0th order equation is pretty straightforward. It says H0 acting on Shayan 0 is En 0 Shayan 0. Of course, this is nothing but the eigenvalue equation for the unperturbed Hamiltonian H0, and this should of course not come as a surprise, because when lambda is 0, H does reduce to H0, and so it's understandable that the 0th order term in the perturbation expansion, the only term which actually survives when lambda is 0, is the same as the eigenequation for H0 itself. And this equation obviously shows that En0 must be an eigenvalue of the unperturbed Hamiltonian H0. This, after all, is an eigenvalue equation. Now, which eigenvalue is this? Could have been any one of them. So, let us say we label things in such a way that En0 corresponds to the eigenvalue epsilon n. So, we have already assumed when we wrote down the notation that there is a way in which I can order the eigenvalues, maybe in ascending order. Of course, ascending order only works when there is no degeneracy. If for eigenvalues with degeneracy, we will have to sort of figure out some other way of counting them, putting them in order. But the point is, epsilon n is an eigenvalue for H0, and we are now looking at how this particular eigenvalue changes when you switch on the perturbation. So, En0 we are taking to be epsilon n. Now, we can have one or two cases. This eigenvalue epsilon n of H0 may be non-degenerate with eigenket phi n. That means all eigenkets corresponding to epsilon n are either phi n or a multiple, which essentially means phi n. So, that is one possibility. In this case, if that happened to be the case, then it is easy to identify what Shayan 0 is. Shayan 0 has to be phi n up to an overall constant which does not matter. So, when we are dealing with a non-degenerate energy eigenvalue for the, remember when I say non-degenerate, I mean non-degenerate for the original unperturbed problem. If you have an energy eigenvalue which is non-degenerate, then starting off the perturbation theory for that is relatively simple, because Shayan 0 is something you already know, it is phi n, the corresponding eigenvalue. Of course, it could be that epsilon n is not non-degenerate, it is actually d-fold degenerate, where d is an integer more than 1. And let us say the corresponding eigenkets are phi n1, phi n2, phi n3 up to phi nd. Then this equation where with En0 equal to epsilon n cannot really tell me what Shayan 0 is. All it can tell me is that the ket Shayan 0 has to be some combination of phi n1, phi n2, phi n3 up to phi nd with complex, possibly complex valued coefficients C1, C2 up to CD, which we do not know as yet. At least the 0th order perturbation equation will not tell you what these coefficients C1, C2, CD are. So, from this point on, our treatment takes two slightly different routes. If we have a non-degenerate energy eigenvalue, what we resort to is what is called non-degenerate perturbation theory. That is simpler to begin with for the simple reason that the unperturbed wave function Shayan 0 is exactly identified already as the ket phi n, the eigenket of H0 corresponding to epsilon n. On the other hand, if epsilon n happens to be degenerate, we have to go in for degenerate perturbation theory, where the problem is that at least at this stage we do not even know what the unperturbed energy eigenfunction is. So, degenerate perturbation theory will be described in a later lecture. For the time being, let us look at non-degenerate case, which is the easier one. So, in the non-degenerate case, of course, this equation, the 0th order equation that we have just been discussing, immediately tells us that En0 is one of those energy eigenvalues epsilon n. Shayan 0 has to be the ket phi n, the eigenket corresponding to epsilon n. Let me point out that for the same Hamiltonian H0, some energy eigenket may be non-degenerate, some other eigenvalues may be degenerate. So, it is not as if degenerate or non-degenerate perturbation theory designation is for a particular system. The particular eigenvalue you are looking at, that decides whether you have to use degenerate perturbation theory, something we are going to describe a bit in a later video, or non-degenerate perturbation theory, the one I am talking about right now. So, of course, if we are doing non-degenerate perturbation theory, then our equations are the same as the ones we have already had. We have already seen the lambda to the 0 equation. So we are only interested in the rest, lambda to the 1, lambda to the 2 and so on. And the important thing is, the only thing that really changes is instead of v Shayan 0 here, we can put in phi n. We already know what the eigenket is. Instead of the en 0 which was sitting here, I can put in epsilon n. So you had a 0 Shayan 1 plus v Shayan 0 on the left, en 0 Shayan 1 plus en 1 phi Shayan 0 on the right. So I've changed this to epsilon n here and phi n here, and I've done that to all the equations here. Basically, on the right hand side, the very first term had an en 0 always, so that gets changed to epsilon n. The last term had en m Shayan 0, that's changed to phi n. Okay, so now let's go on to see what these equations tell us about the energy corrections En1 and the wave function corrections, so the eigenket corrections Shayan1 and so on. So now let us look first at the first order energy correction. For that, we start from the equation with which came from comparing the lambda to the 1 on both sides of the perturbation equation. This of course is the equation where we have already put in Shayan 0, we are sitting here and here as phi n, and en 0 is epsilon n. So our job is to try to find out en1. Now that's actually very easy. All you have to do is apply the bra phi n on the left, from the left, on both sides of the equation. So the bra phi n comes and sits in each one of these terms here. The rest of course is whatever you had in this equation. Now remember, the ket phi n is an eigenket of H0, and since H0 is Hermitian, bra phi n acted upon by H0 dagger by H0 is the same as bra phi n acted upon by H0 dagger. That's the adjoint of H0 acting on ket phi n, and since epsilon n, the eigenvalue, has to be real for a Hermitian matrix or Hermitian operator, sorry, you end up with this term being epsilon n H0, epsilon n phi n Shayan 1. Actually, the first term on the right hand side is also exactly the same, so they cancel. We are left with phi n v phi n, and here of course en1 is just a number, it comes out, and phi n, this overlap is just 1. So we have already assumed, by the way, maybe I should have already mentioned this, but I took it for granted, that for the unperturbed energy eigenkets, the phi's, we have already assumed them to be a complete orthonormal set. Okay, but now that we have done that, it's easy to read off what the first order energy correction is. Simply, the expectation value in the unperturbed eigenstate phi n of the operator V. It's sort of easy to understand this. It just says that to a first order in perturbation theory, the energy correction for non-degenerate energy eigenvalue is simply nothing but the expectation value of the perturbation operator in the unperturbed state. So this is a very, very important result which we will use in applications over and over again. What about Shayan 1, the first order correction to the eigenket? Well, for that we start with the equation, the same equation all over again, but this time instead of hitting with the bra phi n on the left, what I will do is hit with the bra phi m, where m is so phi m could be any arbitrary energy eigenbra for the unperturbed Hamiltonian, not necessarily the same eigenbra as the one corresponding to the energy eigenvalue we are dealing with. The calculation goes more or less the same way. Phi m is 0, of course, is simply epsilon m times bra phi m, and here of course the epsilon n and the en1 being numbers just come out of these matrix elements. So you end up with this result. Now just as a quick check, if you put in m equal to n, what happens is this term and this term just cancel each other out. Right, because now that m is equal to n, epsilon m and epsilon n are exactly equal, and this term simply becomes phi n v phi n, this term becomes 1, so we get back the result that we had in the last slide. En1 is phi n v phi n. For m not equal to n, what happens is this term goes away, right, because delta mn now is 0. So this tells me how to find out the overlap of Shayan1, our first order energy eigenvalue correction, with the phi m. And how much is that? You just move this to the other side and divide, and you end up with this result. Phi m v phi n divided by epsilon n minus epsilon m. Notice that our energy eigenvalue epsilon n is non-degenerate, so it does not match any of the other energy eigenvalues. So this division by epsilon n minus epsilon m is fine. You are dividing by a non-zero number here. So this gives me the matrix, the overlap of Shayan1 with phi m. Now I already know that the phi m's form a complete set. So if I know the overlaps of Shayan1 with every one of the phi m's, I essentially know what Shayan1 is. There's only one catch. The catch is this formula tells me nothing whatsoever about the overlap of phi m and Shayan1 when m is equal to n. Of course, when m is equal to n, this side diverges, but you already know that when m is equal to n, this equation tells me nothing about phi and Shayan1, because phi and Shayan1 just drops out of the equation. So with this in mind, Shayan1 turns out to be this expansion phi m times the phi m Shayan1 overlap value, which is phi m v phi n by epsilon n minus epsilon m. From here, for m not equal to n, but we are left with one more term, phi m Shayan1 with phi times the ket phi n. This is the term which perturbation theory, it is first order perturbation theory, will not tell us what this term is. Okay. So we have found out that the first order energy correction is simply the matrix, the expectation value of V in the unperturbed energy eigenstate. The first order wave function correction is also pretty straightforward, except for the fact that there is an unknown undetermined piece here. Now can we find out this piece by demanding something else about the wave function, like demanding that it's normalized? Perturbation theory cannot determine this term, that's clear. So can we use normalization for this? Well, that depends, in the sense that some authors use what is called intermediate normalization. They demand that all these first order, second order, third order wave function corrections, they are orthogonal to the unperturbed phi n. This is what they demand, which means phi n Shayan1 in particular. This is for phi n Shayan s, for any s. Phi n Shayan1 is 0. Of course, this is for s mode 1 or more. Shayan 0 of course is the same as phi n, and then the overlap would simply be 1. But for all other, for the corrections, Shayan 1, Shayan 2, etc., the demand is phi n is orthogonal to them. So this term simply drops out if you use the intermediate normalization convention. However, many other authors, including the rest of this lecture, for example, we use a more conventional normalization. Okay, this is what you get when you demand the intermediate normalization. So sorry, the conventional normalization has just escaped below the screen. I didn't notice that. Of course, what is being demanded here in the equation, which is invisible to you right now, is that the perturbed wave function, the entire perturbed eigenket Shayan, is normalized to 1. So this is what we are really demanding. Shayan, the eigenket, which remember can be expanded in powers of lambda like this, where Shayan 1, Shayan 2, etc., the first order, second order corrections. We are demanding that this Shayan is normalized to 1. Of course, if you were to normalize this, that means you take the overlap of this with itself, and because lambda is real, it stays lambda when you take the adjoint, but you have to take, but it of course changes, the sum index changes from m to m prime, and if you do it carefully enough, this is what you end up with. Now there is a sum over both m and m prime, but notice that the power of lambda here is m plus m prime. We can change our indices here and change indices from m plus m prime. Let's change that to s. So we switch over to new indices s, which is m plus m prime, and the index j, which now runs from 0 to s. And of course, this is lambda to the s, and when this first coefficient is j, the next one has to be Shayan s minus j, so that the two together add up to s. And this of course is 1, which is the same as lambda to the s delta s0, this power series, because now only the s equal to 0 term, which is lambda to the 0, namely 1, survives on the right hand side, everything else goes away. And just comparing them term by term gives us this as a normalization condition. So if you use the conventional normalization here, the condition that you have to follow is a bit more complicated. Let's just see what this means. Say for example, for s equals, this works for all s, 1, 2, 3 and so on, even for 0, but for 0 you have to get 1, and that's pretty straightforward. If you put in, if you have s equal to 0, there's only one term here, Shayan 0, Shayan 0 again, which is phi n's overlap with phi n, which we know is 1. For s equals 1, what this becomes is Shayan 0, which is phi n, Shayan 1, plus Shayan 1, Shayan 0, that is Shayan 1, phi n. So notice that in the conventional normalization, we don't really get the result that phi n Shayan 1, this unknown piece in Shayan 1, which perturbation theory cannot tell you about. We don't get that as 0. All we get here is that it when added to its complex conjugate is 0, which means it has to be purely imaginary. That's all you really get. For s equal to 2, you get something slightly more complicated. You get phi n Shayan 2 plus Shayan 1 plus Shayan 2 phi n. Remember, the phi n is Shayan 0. So this is really Shayan 0, Shayan 2, Shayan 1, Shayan 1, Shayan 2, Shayan 0. All the 3 ways you can add up to non-negative integers and get 2. Of course, for s equal to 3, it will be Shayan 0, Shayan 3, Shayan 1, Shayan 2, Shayan 2, Shayan 1, plus Shayan 3, Shayan 0. 4 ways and so on. And this has to be 0. So this one, for example, tells you that the imaginary part of phi n Shayan 2 is related to this overlap Shayan 1, Shayan 1, and so on. Now let us take a look at the second order correction. Well, we start from the second order equation, the equation you get from lambda square. What you get is h0 acting on Shayan 2 on the left, plus v, which has only one lambda, times Shayan 1 acting on Shayan 1. All on the left, these are the two terms you get. These are the two terms which will give you lambda square. On the right, 3 terms give you lambda square. En0, which we now know is En epsilon n, Shayan 2, En1 times Shayan 1 plus En2 times phi n. So aim here is to find out En2. Well, let's start by hitting both sides by the bra phi m. Right? If you do that, the right hand side is pretty easy. All these numbers, epsilon n, En1, En2 are just numbers. They come out and you directly end up with overlaps. On the left, this one becomes epsilon m times phi m. So this is also a simple overlap. And if I just move this term, which is epsilon n phi m Shayan 2, to the other side, you end up with epsilon m, which came from here, minus epsilon n, which came from here, phi m Shayan 2 plus phi m v Shayan 1 equals en1 phi m Shayan 1 plus en2 delta mn. Now, to find out en2, all you have to do is put in m equal to n. But we could have done that at the very beginning. If I do this, then this phi m Shayan 2 term just drops out. By the way, if you want to now know what Shayan 2 is, find out the second order energy correction, eigenfunction correction, you will actually need to know what these overlap values are. And for that, all you do is put m naught equal to n. Then this term en2, the unknown en2, will drop out. And then you will be able to find out phi m Shayan 2. For the time being, we want to find out en2. So put in m equals n. Then because of this factor, this unknown term drops out, and you are left with en2 is simply phi n v Shayan 1 minus this term en1 phi n Shayan 1. Of course, if we were using intermediate normalization, phi n Shayan 1 would be 0, so this term would simply not be there. Now this looks like a bit of a problem, because as we said a while ago, phi n Shayan 1, what this overlap integral is, this particular one, the one corresponding to m equal to n, cannot be found from perturbation theory. So it looks like our formula for the second order energy correction has a piece which perturbation theory simply cannot tell you about. So how then can we claim that perturbation theory allows us to calculate the energy correction? I have a nice formula for en2, but there is a piece there which cannot be found out by perturbation theory itself. In fact, the intermediate normalization told us if we were to adopt that, this would be 0, but that would just be a convention. Real measurable values like energy eigenvalues should not depend on which convention you are following. And if we use the conventional normalization, then phi n Shayan 1 is not even 0, it's a purely imaginary number. Of course, that should also give us some reason to worry. After all, en2 is a second order correction to a purely real quantity, the energy eigenvalue en. en1 is also real, right? It's just the energy expectation, the expectation value of V, a Hermitian operator, in the state phi n. So this looks like a purely imaginary term and should not have any place in an expression for en2, which should really be real. So let's see whether we can resolve all these issues. Two issues are there really. One is that this unknown thing, something which cannot be determined by perturbation theory, is there in a formula for calculating second order energy correction. That in itself should be a problem, and it's perhaps an even, well, not even bigger, but at least a problem of the same magnitude, that if we were using conventional normalization, then this term will be purely imaginary, and you apparently have a purely imaginary term in something which should be real. Well, to understand this better, what we do is use a resolution of the identity. Remember, the ket phi m's are assumed to form a complete set of orthonormal vectors. So this is the identity, and we just insert the identity in this expression. So this is exactly the same expression as the one up here, except that we have inserted the identity in between V and Shayan 1. This of course breaks up into this space phi n V phi m Shayan 1, where the sum over here is all over all m. Of course, from this you have to subtract this troublesome term that we have been worrying about. Now notice that this whole sum can be split into two pieces. The piece where m is not equal to n, majority of the terms of course, that's just this term here, plus one more piece where m is equal to n. But what is it when m is equal to n? Phi n V phi phi n Shayan 1. So we club that along with this term and take this factor common. I end up with this result. And now we see why this troublesome term does not really cause us any bother whatsoever. Phi n v phi n, we figured out a while ago, is nothing but en1. So this term is really 0. So the fact that we could not figure out what phi n Shayan 1 was from perturbation theory actually has no bearing whatsoever in the final result for en2. The final result is independent of this extra piece. And we are left only with the m not equal to n term. Now we use the fact that we already know what these overlap values are. Remember, we know them only for m not equal to n. And we plug this in. Notice phi n v phi m may very well be a complex number. Phi m v phi n could also be a complex number, but these two complex numbers are conjugates of each other. So their product, of course, is a modulus square, which is definitely a real number. So this is the final result for the second order energy correction. The m nth matrix element of V, this bra phi m V ket phi n, the magnitude squared of that goes in the numerator of the expression. The denominator just has epsilon n minus epsilon m, the energy difference between the other states which are there in the sum and this unperturbed energy eigenvalue epsilon m. So some remarks here. Up to second order in perturbation theory, En simply turns out to be epsilon n, which is, of course, this is, here we are putting back lambda equals 1. So En, so we have the full Hamilton H equal to H0 plus V. The nth energy eigenvalue En turns out to be epsilon n, which is, of course, En0, plus Vnn, which is En1, plus Vmn mod square by epsilon n minus epsilon m, summed over all m not equal to n, where Vmn, of course, is nothing but this shorthand. And Vnn, of course, is phi n v phi n, the expectation value in the nth energy eigenstate. Now, when is the second order correction important? Well, if the first order correction vanishes, of course, the second order correction becomes all important. Even if the first order correction did not vanish, the second order correction would actually could become pretty big. Remember, Vnn is or Vmn's in general are matrix elements of the perturbation V, and we are assuming that in some sense V is small compared to H0. So in most cases, V's are small compared to the epsilons, the Vmn's. Which is why this second order term, which is square of such a matrix element, would typically be much smaller than the first order term, which has only one Vnn. Of course, if the first order vanished, as we just said, this would have to be important, because then that's the lowest non-trivial correction you have. But there's another situation when this term might become very important, which is when you have a nearly degenerate energy level, that is epsilon m is pretty close to epsilon n. Then you have a very small denominator here for at least that term, and then this sum, at least a few terms of that sum, even if only one term, might become a pretty important big thing. So when you're close to achieving degeneracy, when your spectrum is close to being degenerate, the second order correction may become very, very important. Of course, if you have exact degeneracy, then epsilon n minus epsilon m will be 0, but then you will not be able to use this method so far that we have been using so far. You will have to modify the method a bit. So if there is an energy level very close, a different energy level very close to epsilon n, the second order correction may become very important. So in many practical applications, it so happens that for most of the regime you can actually ignore the second order term, but suddenly the second order term becomes important because you're getting close to a degeneracy, and there this can have all kinds of interesting physical effect. Now another result that we get is, if you consider the ground state but n is 0, the second order energy correction is Vn0 m0 mod square by epsilon 0 minus epsilon m for all summed over all m, which is not 0. Sorry, this should be m not equal to 0 here. Now, notice that for all m which are not 0, epsilon m is actually more than epsilon 0. After all, epsilon 0 is the ground state energy. Any other epsilon is more than that, which means that every term in this sum is negative, and so for the ground state, the second order energy correction is always negative. That's another important point. And the point that we have been stressing, the indeterminacy in the first order corrected wave function Shayan 1 does not affect the value of En2. And not only that, if we try to find out Shayan 2 just by using the same technique as before, instead of putting m equals n, use m different from n, and we get phi m Shayan 2 and so on, we will see that there are certain terms that you cannot find. But this lack of knowledge about certain terms will not lead to any problem when you try to calculate En3 or En4 or so on. Not only that, it can be shown with a bit of effort that not only does this lack of knowledge about certain parts of the corrected wave function not make a difference to the energy eigenvalue calculations or correction calculations, they will not make any difference in physical expectation value calculations as well. So the fact that we cannot figure out certain pieces of the wave function from perturbation theory will make no physical difference whatsoever. Now, in the next lecture, we are going to look at a trick which will make calculation of higher order energy corrections slightly easier, and then we are going to go on and discuss degenerate perturbation theory. Bye for now.